So it's a pleasure for me to introduce Dr. Jaeyeon Lee, who came from Princeton University. So Jaeyeon got his PhD, his undergraduate and PhD at Seoul National University in Korea. So he got his PhD, I think, last December. This February, okay, it's wrong. So, and then he came over to work as a postdoc at GFDL, working on a project that I'm collaborating with Xiaosong Yang at GFDL. So his PhD work was on East Asian Extratropical Cyclones. So that's actually what he will be talking about today. So without ado, let him start. So.
Thank you, everyone. Thank you for introducing me, and thanks for attending this talk. Everyone. I'm so glad to give a talk about my previous research to great faculty and talented students in Stony, Brook University. So, yeah, I'm Jaeyeon Lee. I'm a postdoc in Geophysical and Princeton. Yeah, the title of my talk is East Asian Extratropical Cyclones and their future changes. This work is I worked on this project with my PhD supervisor So in Seoul University and Professor John Trum at Macquarie University. Yeah, let's start the talk. Eccentric cyclone is a large-scale atmospheric turbulence mixing, enhancing mixing. The left figure is volcanic life cycle experiment using idealized QZ model. Initial temperature gradient is elevated through converting potential energy into kinetic energy, and this kinetic energy intensify wave, and this wave become closed system like cyclone and anticyclone. In real world, these cyclones can transport mass, momentum, energy, and especially water vapor forward and upward, and it stabilize stratification and moderate temperature gradients. In particular, these mid-latitude cyclones ascend some moist air and condense its moisture, and through this process, these cyclones occur local precipitation and mid-latitude. So this information implies that the extratropical cyclones can exist at any middle latitude if there is strong volcanicity, and they can affect the local precipitation. So East Asia is also the region where the strong volcanicity exists. This is world population density map. Here is East Asia. This East Asia is highly populated regions, and I came from this black dot. This is Seoul. This is the night view of Seoul. I came from here. If you have been Seoul, you can know, you can realize Seoul is highly populated regions, but there is very beautiful. But yeah. Anyway, East Asia is located upstream of the main storm trend regions, but their weather impacts are closely related to extratropical cyclones. This is SFT and operable wind and balcony city in East Asia. East Asia has a strong SSD gradients resulting from conflict between cold oaxial current and warm crucial currents. These strong SSD gradients enhance balcony wind shear through thermal balance, and it increases volcanicity. So, and East Asia has also two huge mountains, Alpine Mountain and Tibetan Plateau. Those two mountains provide some favorable condition for cyclogenesis and in their downstream regions. This background field in East Asia indicates many extratropical cyclones can be generated in East Asia, and they can intensify strongly in East Asia. This is cyclone's contribution to northern hemisphere total precipitation. As you can see, cyclone's contribution is higher in winter season than in summer season. And over 70% of precipitation in most of middle latitude is associated with extratropical cyclones. In East Asia, extratropical cyclones has high contribution to local precipitation in this region. Due to this importance of East Asian cyclones, there have been the efforts to understand East Asian cyclones climatology. This figure shows East Asian cyclones mean trends and their genesis. So Adachi and Kimura 2007 and Jaeyeon 2012. They suggested East Asian cyclones are generated over the land mainly, and they pass through populated regions. They highlighted the importance of East Asian cyclones, but the detailed cyclone properties like their development process or their seasonality were not fully explained at that time. So the study, this regional study on this detailed cyclone properties was needed. And as the impact of global warming has been reported, so there has been the efforts to understand extratropical cyclones' response to warming climate. Left figure is future change of cyclone frequency at northern hemispheric cyclone frequency at hemispheric scale, and right figure shows their spatial distribution. Many previous studies suggested that at the hemispheric scale, extratropical cyclone may decrease in a warming climate, but these changes are shown differently in each regions at the regional scale, like as shown this. Due to this regional dependence, sorry, it's okay. Due to this regional dependence, there has been many previous studies of regional cyclones future change in a warming climate, especially in North America and Europe. However, that kind of study was not well documented in East Asia. So it is natural to raise questions like this. One is, what general features do East Asian cyclones have? The other is how change these cyclone features in a warming climate. My previous studies try to answer these questions. In this study, I use a Lagrangian approach for considering individual cyclones features and their its weather impact. To do this, I used automated tracking algorithm developed by Reading University. So in this algorithm, cyclone is detected by on 850 Pascal pressure level relative vorticity field, and the cyclone center is defined as local maximum. And I consider only moving cyclones which have a minimum intensity of 1 CDU, travel at least 1,000 kilometers, and maintain at least 2 days. This is the East Asian cyclones climatology. East Asian cyclones are the most active in West Siberia and Mongolia and crucial Oyashio extension. These East Asian cyclones are mainly generated from downstream of 2 mountains and over the crucial Oyashio extension, showing strong volcanicity. According to their genesis locations, they are called as Mongolia cyclone and East China cyclone and crucial cyclone. These East Asian cyclones pass through a travel eastward, and they intensify rapidly over the crucial Oyashio extension, and they decay rapidly near Kamchatka region. These East Asian cyclones have an exclusive seasonality. This is seasonality of East Asian cyclone frequency. Typically, extratropical cyclones are most active in winter season, which shows the strongest volcanicity. However, some continental cyclones, like Mongolia cyclones and East China cyclones, they are most active in spring season rather than not in winter season. I investigated these continental cyclones development process, showing exclusive seasonal variability. Left column is the vertical structure related to Mongolia cyclone, and right column is upper and lower level potential PV anomaly and IVT anomaly, and the 2 PV right. So from incipient stage of Mongolia cyclone development, they interact with strong upper trough, and they intensify with this strong vertical interaction. These strong upper forcings are shown as upper PV anomaly. You can see the upper PV anomaly, positive upper PV anomaly, and some tropophilic body near surface Mongolia cyclones. It implies that this upper forcing is highly important in Mongolia cyclones development. East China cyclones has a different development process to Mongolia cyclones. East China cyclones have shallow cyclone structure without any strong private trough signal. However, they have the strong diabatic heating at their middle level. This strong diabatic heating is related to the strong moisture convergence within East China cyclones, and this diabatic heating through this process of positive potential vorticity anomaly is located at the middle level, and it enhances the lower level cyclonic circulation. So it means that the diabatic process at the low level plays a major role in developing East China cyclones. These two East Asian cyclones have not only different development state, development mechanism, but also different weather impacts. This is East Asian cyclones weather impacts. Left column is severe pressure anomaly related to Mongolia cyclone 3 days before the occurrence of yellow dust events to onset day of yellow dust events. And right column is East China cyclone's mean position and their related precipitation. So the Mongolia cyclones generally they pass through Gobi Desert and they transport yellow dust from this desert and to Korea and Japan. This is highly this is very important weather events in especially in South Korea. And East China cyclones transport a huge amount of moisture from subtropics to East Asia, and through this process they occur precipitation of East Asia. These East Asian cyclones have also significant long-term trend. This is the long-term trend of East Asian cyclones frequency. Springtime East China cyclone and summertime Mongolia cyclones have negative trend, negative long-term trend during from 1979 to 2017. So interestingly, this negative trend of East Asian cyclone in the observation is somewhat consistent with the projected change of East Asian cyclones in warm climate in semi models. Detailed models results will be shown in next slide. So far, we discussed about various features of East Asian cyclones in the observation. Because extratropical cyclones, as I mentioned before, extratropical cyclones is very important weather system in East Asia. So it is essential to understand how they will change in a warming climate. So I evaluated the Sim5 model's performance for simulating East Asian cyclone properties, and then I explored future change of these cyclones in warming climate. In this study, in this part, I use 9 Sim5 models and 6 Sim5 models with no missing values of topography over mountains. Actually, the missing value of a mountain could occur some deficit, high deficit of the extratropical cyclones in automated tracking algorithm. So yeah, so that's why I choose these models. And I use historical loss and RCP 8.5 and SSP 8.5 runs. And in precipitation part, in future change of precipitation part, I used 4 underlined the models providing 6-hour precipitation data in both historical and SSP 8.5 runs. This is simulated East Asian cyclone frequency in Sim5 models. Contour shows East Asian cyclone frequency in each model, and shading is model biases. Overall, the C5 models qualitatively well reproduce spatial distribution of East Asian cyclone frequency. Yes, sorry. East Asian cyclone frequency, and however, there are still systematic bias. Most cyclones, most models overestimate the cyclone frequency nearby high terrain regions, and they underestimate cyclone frequency over the ocean. These model performances are summarized in Taylor diagram. This Taylor diagram, using this Taylor diagram, you can quantify models' performances using pattern correlation and standard deviation and mean squared error. So from this Taylor diagram, we can select the 5 models showing better performance than other models, and we used these best 5 models for exploring future change of East Asian cyclones. This is East Asian cyclones in our warming climate. So the best 5 models project reduction and weakening of East Asian cyclones in our warming climate. Especially this reduced cyclone frequency is partly contributed by this reduction of cyclogenesis in downstream of Tibetan Plateau. To understand this future change, we investigated the volcanicity change in a warming climate. This is future change of volcanicity in East Asia. This volcanicity, in this study, volcanicity is measured by this ED growth rates, and the left figure is the temperatures. As you can see, the ED growth rate is weakened in downstream of Tibetan Plateau and over some part of the ocean. So this region is the upstream region of reduction and weakening of East Asian cyclone in our economy. So it implies that this weakened volcanicity could contribute to the future change of East Asian cyclones. The ED growth rate is a function of wind shear and static stability. And this ED growth rate in RCP period can be decomposed into their historical value and plus their change. So using approximation, we can get this approximation. So from using this equation, we can get some the volcanicity change to wind shear alone and due to static stability alone. So using this equation, we can investigate those 2 volcanic components contribution to volcanicity change in a warming climate. This is the result of this approximated equation. First, you can see that this approximation is quite similar with the left hand figures as shown before. So and middle and right figure shows these two Barkley components contributions, and wind shear induced the weakening of ED growth rates downstream of Tibetan Plateau, and static stability also contributes to ED growth rate change the downstream of Tibetan Plateau, but they are more contribute to over the oceans, the Barkley change over the oceans. And we simply confirmed the robustness of our CNIF5 readers by comparing with CNIF6 readers. So the lower column, the lower panel shows CNIF6 readers on future change of East Asian cyclones. CNIF5 and CNIF6, they project a reduction of and weakening of East Asian cyclones, although they have some uncertainty, especially future change of uncertainty for the East Asian cyclones future change over some part and some part over the ocean, and the location of main reduction of cyclogenesis in a warming climate. These cyclones future change can be an important implication to regional hydrology because the extratropical cyclone is one of the weather phenomena determining local precipitation. So, yeah.
So is this the annual average or for particular?
These all results are annual means. So, but I found these annual mean results are very robust throughout all months. So I can show you. So this is the seasonal dependence of the annual results. So left and right is future change of cyclone frequency and intensity of East Asia. So you can see the red dot. So throughout all months, you can find a reduction of cyclone frequency and weakening of cyclone intensity. So yeah. So okay. Yeah, this is the future change of cyclone precipitation using CNIF6 model. So, and I focus on wintertime precipitation change because East Asia, as I shown before, East Asian cyclones highly contribute to wintertime precipitation. So yeah, that's why I choose this season. So the cyclone frequency, cyclone precipitation, right column is cyclone precipitation change, and left column is total precipitation change. Many previous studies suggested that in a warming climate, atmospheric moisture content will increase, and this increased moisture content could lead to enhanced precipitation in a warming climate. So as you can see that the cyclone precipitation in a warming climate is projected to increase in most of East Asian region, except the region where the strong decrease of cyclone frequency is projected. So, and this decrease of cyclone precipitation could contribute to the decrease of total precipitation up to 20% of the precipitation in these regions. It implies that this increased moisture content in a warming climate could offset by future change of extratropical cyclones, East Asian cyclones in a warming climate. And he also investigated the extreme cyclone precipitation's response to warming climate. So extreme precipitation is defined as over 95th percentile in each grid point and in history column. Extreme total precipitation pattern is quite similar with the total precipitation pattern. So, and interestingly, in a warming climate, the extreme precipitation is projected to increase, especially near the east coast of East Asian continent. And however, extreme cyclone precipitation pattern is quite different with their cyclone precipitation pattern. So the strong extreme cyclone precipitation is located near Korea and Japan. It means extreme, and in a warming climate, this extreme cyclone precipitation is projected to increase, especially near Korea and Japan, of these East Asian populated regions. So, to understand this extreme cyclone precipitation's future change, I investigated the relationship between the cyclone and the cyclone precipitation in a warming climate. This is this figure shows the number of cyclone frequency with their intensity, and the upper PDF is the cyclone precipitations change in a warming climate. In a warming climate, the blue line is historical loss regions, and red line is warming climate simulations regions. So we can moderate the cyclone precipitation is decreased in a warming climate. However, the extremely intense cyclone precipitation is projected to increase in a warming climate. And interestingly, moderate and weak cyclones number is projected to decrease, and their extremely strong cyclones number is projected to increase in a warming climate. So this research indicates that the cyclone precipitations change is closely related to could be closely related to future change of East Asian cyclones. And from this joint PDF, it is confirmed that even with the same intensity of cyclones, cyclones in a warming climate simulation can cause more precipitation than in historical simulation. I think it could be due to the increased atmospheric moisture content in a warming climate. This research implies that the weak and moist weak and moderate cyclone precipitation could be contributed by the number of weak and moderate cyclones. But the strong precipitation could be contributed by both changes of cyclone number and atmospheric moisture contents in warming climate. My summary. East Asian cyclones are mainly generated by recyclogenesis downstream of those East Asian two mountains and coastal cyclogenesis across crucial glacial extension, which showing strong acidic gradients. And interestingly, East Asian cyclones are the most active in winter season, not in spring season, not in winter season. And these East Asian cyclones are simulated qualitatively simulated well in CME models, but there has some biases, especially the overestimation near high terrain regions and its downstream, and especially underestimation over the ocean. And CME climate models project reduction and weakening of East Asian cyclones in warming climate, and it seems to be related to weakened volcanicity on their upstream. And these future changes are corresponded with to projected decrease in relatively weak cyclone precipitation from near Korea and Japan. And extreme precipitation is projected to increase over East Asian populated regions. It seems to be associated with projected increase of extreme cyclones and enhanced moisture contents in a warming climate. This is my end of my presentation. Thank you for thank you and thank you.
Okay, the questions. Actually, let me ask the first question here. You said that East Asian ETCs are strongest in spring, not in winter. So have you looked at the reason why? Have you investigated that?
Yeah, actually, I didn't publish about that, but I investigated about that before. Actually, as you guys know, midwinter suppression, it seems to be related to midwinter suppression over North Pacific, but the midwinter suppression is focused is located in the midwinter suppression is related to any activity over the North Pacific, but it is upstream of their upstream, right? So yeah, but that is this exclusive seasonality seems to be related to their possible causes of that midwinter suppression, because I can find some very strong jet stream in East Asian regions. So it could be, and this jet stream is a little bit shifted downward at the southward. So it could be occur some the weakening of vertical interaction between the surface cyclone and upper trough. So it could be it could lead this exclusive the seasonality. So I think so. So, but I need to examine that more. So specifically. So yeah.
Yeah, okay.
Yeah.
Hi, I'm curious, maybe if you could go back a slide and look at, you showed the joint PDF of intensity and rainfall. Do you have a sense for how, so in your summary there, you talked about how the models can well represent, right, these storms. But I'm curious if you made any analysis of comparing this joint PDF of the historical to observations.
Actually, I didn't bring that figure, but I did. But yeah, in the model, cyclone precipitation efficiency is much lower than than observation. So I don't know why, but yeah.
So that's interesting because it means that you have to take at least the simulated change in precipitation intensity with a little bit of a grain of salt, right? Because if there could be process while these storms are well resolved to some extent in climate models.
You're right.
The subcirculation, such as fronts that are producing the extreme precipitation, right, or even mesoscale systems within it, are not well resolved, and so that could be. So it's possible that the changes at the extreme might actually be larger in reality.
Yes, that's a very interesting point, and that is one of my ongoing projects in Geophysics. So yeah, I can give you an answer maybe later.
Yeah, so about the weak bioclinicity over East Asia, the wind component, the wind shear component, is it related with the migration of the jet or just a reduction of the shear, specifically downstream of the Tibetan plateau?
So you're saying, warming climate?
Yeah, in the warmer climate,
Yeah.
is it because of the migration of the westerly?
Yeah, actually, that is not related to the latitudinal shift of jet. So it is just a local weakening of private jet. So it is related to I missed so many information. So that. Sorry. I found the jet is the upper wind is locally weakened in this area. It is related to meridional circulation on the tropics. So I found that the tropics overturning circulation, meridional overturning circulation is locally weakened in this area. So the southern part of this area. So the meridional overturning circulation, if meridional overturning circulation will weaken, then the upper jet, their related upper jet should be weakened, right? So yeah, that is related to tropical change.
Thank you.
Yeah, since you are at this figure, so I have a question about. So for the stability, what levels did you calculate the static stability between?
The 800 from 850 hectopascal to 500 hectopascal. So yeah.
Yep. So yeah, there are talks about a decrease in static stability, but it's actually quite prolonged here. So have you investigated why the static stability seems to be decreasing so much over that particular region?
Yes,
there?
I think that is. I didn't examine. I didn't do additional analysis, but I think that is related to some increased moisture over the ocean. So it could be some the moisture adiabatic rate. It could be some could make some stable in the atmosphere. So yeah.
Yeah, but we usually use that explanation for tropical region.
Yes.
Mainly
right.
because it's only at the in the tropics that you have the moist adiabat.
You're right.
And if you just look at the zonal mean temperature profile is near the tropics where you get this clear upper level amplification that give you a reduction in static stability. But here you are at 40 degrees and it's kind of local also. It's not widespread. It's not
So yeah, you're right. So yeah.
So, well,
We can.
yeah, I'm confused by this figure too. I mean, if you have reduced baroclinicity, which implies reduced frontal structure, you imply that you have a weaker stability, right? I mean, a frontal zone is a stable zone. You know, if you look at the vertical. So if your frontal temperature gradients are weakening, that would imply a weaker stability, at least in my view. Because you know your isotropes are not as. So that, I guess I can think about the right one. I'm still confused about the shear because if this baroclinicity is decreasing, I would expect from thermal wind the shear to decrease more when you break this up. So I'm more confused about the middle panel and why that signal is not as strong. Reduced shear. If there is reduced baroclinicity, and I've never broken apart the EV growth rate like this. I've just assumed almost that it was coming primarily from the shear at mid latitudes. So it's kind of a
actually that is I thing to quantify exactly even the ocean quantify the exact baroclinicity. So yeah, you know, we can calculate only the wind shear which already affected by some various atmospheric factors, right? If you use GCM output, so yeah, you're right. Yeah, sometimes it's very complex. Yeah.
But just to follow up on something, so if I understand your conclusions, decreased baroclinicity, the cyclones are weakening, there's more precipitation, so that additional latent heating and PV generation from latent heating is not fully compensating the baroclinicity impact from your results. So you're seeing a precipitation signal, but that is not ultimately compensating for the lack of for the reduction in baroclinicity, at least in the climate model world.
Sorry.
I'm just trying to summarize your conclusion slide where you have your baroclinicity decrease, right, which you showed. Reduction, and then there's reduction and weakening of the extratropical cyclones. But then, you know, typically there's an offsetting term, right, for latent heat, precipitation, and increasing cyclone intensity.
Yes.
And there's this shift in precipitation anomaly and more positive, but that contribution to the cyclogenesis is not compensated. It's not fully, compensating the loss of baroclinicity. Right. So, which is I'm not sure how general that result is in other parts of the world. I always thought that there was a more equal. That latent heating is very important.
Well, I think he did show that the extreme cyclones do seem to have increased a little bit. If you won't go back to the joint probability, one, the tail of this seems to have increased. So that might be the impact of the precipitation of the latent heat. But I think the number of cyclones is decreased everywhere. So that's a very, very robust result. And we attribute it to decrease in baroclinicity. So that's the attribution, but obviously it's very difficult to to really figure out what the real reason was. But it's even the case, even if we go down to a quarter degree model, it's still, so it's not just, it's not due to poor resolution. Obviously, quarter degree still not resolving all the mesoscale structure, but the reduction in cyclone number and general intensity is very robust across all models. So it seems that even down to a quarter degree, the increase in latent heating is not compensating for the volcanicity, I think. But any other questions? Okay, if not, then let's thank the speaker again.